It looks as if we're all here. So for those of you who don't know who I am Ken Evans, and I am a Pro Vice Chancellor, and I am the Dean of the College of Engineering, Mathematics and Physical Sciences. And it is with great pleasure that I am here to introduce this evening's speaker. And Inspiring Science is an open lecture series that we run in which distinguished speakers from inside and outside the university speak about their research and careers in their respective scientific fields. And the series includes inaugural lectures from the college. And this evening we have the inaugural lecture of Professor Ronaldo Menezes, titled On the Scale, Concentration and Dynamics of Crime. Now, clearly crime is a very serious and important issue for society, and Ronaldo will present some of his fascinating work on describing, characterising and to some extent maybe addressing this problem. And as the Dean of the College, I'm very pleased to be able to introduce Ronaldo to you all. He has only been with us for about a year, both as a Professor of Data and Network Science and Head of Computer Science. And on a personal note, I would like to say how much I am enjoying working with him. And he has brought with him from the US new perspectives, fresh ideas, and very much a can-do attitude, which I'm very much appreciating. So thank you for that, Ronaldo. In fact, Ronaldo began his career with a PhD in computer science at the University of York, which he completed in 2000. He then spent a brief period at the University of Ulster before moving to the Florida Institute of Technology, where he spent 18 years building a distinguished career to full professor before deciding to make the jump here. Ronaldo is a member of many professional organisations. He has served on several key steering and policy groups overseeing various aspects of computer network development. He is a board member of the Network Science Society, and he is a co-editor-in-chief of the Applied Network Science Journal. His research is on network science, i.e. complex networks, bio-inspired computing, complex systems and human dynamics. He has more than 150 peer-reviewed publications and has collaborated with more than 40 researchers worldwide. I could go on, but actually you are here to listen to Ronaldo rather than me. So please join me in welcoming Professor Ronaldo Menezes to speak on the scale, concentration and dynamics of crime. Ronaldo.
All right, so I thank you all for being here, right? So I was telling Ken before outside that I never gave an inaugural lecture before, and I'm hoping this is the last one I will have to give. Because it costs money, right? So I didn't know that part when they asked me to.
It's in the small print.
So I'm trying to make sure that I use my money wisely. So because I never gave a lecture like this, I'm gonna try to tell a little bit how I got here, right? So in terms, not how I got, I mean, I flew here from the US, but how I actually got here in terms of a career. So I will start basically telling where I come from, right? So if this, it's gonna work now. So yesterday I was actually trying to find a map of the world, and then somehow you're gonna maybe enjoy this. I didn't just want to put like the world map, the atlas there, and I said, well, I think I Googled something like interesting maps of the world. Okay? And then this came up, and I thought it was nice, a hand draw. And that red point is where I come from. I was born in Fortaleza in Brazil, northeast of Brazil. I'll show you some pictures in a little bit. But because we suppose in academia to be inclusive and show other ways of addressing the same or showing the same point, I also found this map, right, for the flat earthers here, that basically shows where I am. And I said, well, I guess if I'm going to say where I'm coming from, I have to say in many different ways. And then I found this one as well, which you should watch the video. It's amazing, right? The moon actually goes through the hole of the torus. But I couldn't find where I actually come from in that one. So I'm assuming I'm somewhere where the question mark is. But anyway, so I prefer to actually show in a more serious way. So I said, well, I like networks, right? So this took a long time, by the way, so to do. So we are connected in many different ways. So, and I come from that little corner there. And I studied my academic career in São Paulo. So I did my bachelor's in Fortaleza, and then I went to São Paulo, which is somewhere there. And never realized that I drove many times. And it sounds crazy. I could tell you a story. Maybe I will tell you this story. That when I moved to the UK to do my PhD, because I drove this so many times, and it's exactly from my house to my house in this city called Campinas, was 3,333 kilometers, right? So, and that I thought that was very amusing at the time. But I did this 3 times a year. So when I moved to the UK, I'll never forget my supervisor, who unfortunately passed away last year, 2 years ago, I think, actually. When it was 5 o'clock, about this time, and I moved, I left my office, and I said, I'm going to go to Cambridge because I need to buy an amplifier. And they said, oh, you're spending the weekend? I said, no, I'm just going to drive there, get the amplifier, come back. And they said, no, it's too far. And I said, well, no, it's not too far because that is what I'm used to drive, right? 3,333 kilometers. But tells you that you change cultures and you have to adapt. But despite that difference, we still all connect. Fortaleza is very nice, right? So I could tell you that this is how it looks like, and it does look like. Of course, there are its problems. It looks like this, all like that. That's where we go every weekend. I could also tell you about the cultural differences in terms of when I came here to the UK, that people said, do you have winter clothes? I came during summer, August. And I said, what is winter clothes? I have clothes, so I don't know what winter clothes are. Because it's like this every year round. Right? So there's a time of the year that rains, and there are times that it doesn't rain, and one last one at night. Anyway, but I came here to talk about my work, right? So I'm gonna try to very quickly tell you some of the things I did in the past, and then I promise I will talk about crime. Okay? So this is again it was hard to find this because I don't really know how I found it. But this was the first paper I published. Right? This was actually a small workshop in Brazil. The worst experience of my life. I'll tell you this in another time because I prepared everything in English, right? So it was an international conference. When I got there, they told me, oh, 80% of the audience they are Brazilians. So can you say in Portuguese? And I mean, how can you have your mother tongue be in Portuguese and you say no? Right? Well, but I never learned any of those terms in Portuguese. So again, it was my first and worst presentation ever. I hope this one doesn't beat that. But this was absolutely an awful experience. So finding it brought back some memories that I didn't want to have. But that was my first paper, right? And then I did several things. For instance, I worked on tuple spaces. My PhD was on garbage collection, so I was trying to track information, how they link to each other, to see if I could actually garbage collect them. After I left, I got interested on the implementation of those systems called the coordination systems, particularly Linda. So we proposed this thing called Swarm Linda that the idea was from the outside, everything looked exactly like the normal Linda system that at the time was actually somewhat famous, but internally everything was based on swarms where the information is stored. And then, like it happened many times, I was trying to solve a problem in Linda, but the way I solved it was more interesting than Linda itself, so I actually started looking at patterns of ants, right? And algorithms on how ants actually spread around. Then I use those patterns to solve practical problems. I mean, this doesn't tell you anything, but on the right-hand side, this is actually a way to do software testing, right? So we use ants to find bugs in software, and what you see as this 2D matrix there are parts of the software and how many times they actually being tested, rather than having concentrations and do this somewhat randomly. Then I said, oh, I like patterns, so we decided to do things related to terrain coverage. And then finally, at some point, I'm already in, I think, 2005, I said, well, I like patterns, so maybe I should look at patterns in crime, right? And I'll come back to this picture in a little bit, right? Because this is how I actually got into network science. It has nothing, no networks at this point, but this picture will come back later on in the presentation. Okay, so jumping from 2005 to 2009, because of this picture and because of what didn't work in this picture, which will come, as I said, later, I got very interested in social networks. Right? Okay, so let's improvise. I'll tell you this picture now, and then I can skip them. So what we were trying to find is that when I was in Brazil doing this work on the software engineering and software testing and how to use swarms to test software, I got approached by a colleague, and this was in Brazil, because I spent a year in Brazil, I took a leave of absence, and they said, look, we have this problem of trying to model where crime is taking place, so do you think you could help? And I said, yeah, I mean, sometimes we think that we can solve every problem, right? And then I said, well, it's very easy, right? It's the same thing as ants trying to find food, criminals looking for places where they commit crime. So I said, yeah, no big deal. So I said, sure, I think we have a way to model this. The problem is it didn't work. It actually was horrible. Right? What we were trying to, we had a lot of data from about crime in Brazil, and it was not even close, which gave us pause to think, and I said, oh, what is missing here? And what was missing is that because in swarms, and some of you work on swarms, the communication is through the environment, right? So if you look at an ant leaves some information here that serendipitously will be found by some other ant at some point. And that's not how criminals work, right? I mean, they learn information from external sources. I guess they read something or they watch the telly, but they also talk to each other. And turns out that at that time we had data about who committed a crime with whom. So we decided to implement this in the model, and it became really, really nice. Anyway, that was, for me, it changed what I got interested in. The same way that I was interested in Linda, went to swarms, and because I was interested more on the solution of the swarms and kind of forgot Linda completely, this basically made me come back to Florida and said, I'm really intrigued about this networks things and how things are connected. So I had my sabbatical actually scheduled to go to Brussels to work with Marco Dorigo. And then I called Marco, he's a good friend, and I said, I'm sorry, man, I'm not going. And then I called this guy because I said, who's the primarily network scientist in the world? And this guy called Laszlo Barabasi. So basically I emailed him, and then we had a call. And I said, look, man, I know nothing about network science. I just need a chair and a desk, right? So can I just sit there for a while? And then I explained this problem I was trying to do, and I said, yeah, sure, come. And then again, I started using networks. So my first work was this one in network science. We took this data from Enron. Some of you are old enough to remember that, right? I'm not, but my student told me about that, and I said, oh, that sounds like an interesting problem. So what we're trying to do is to say, all right, so what if we don't look at the content? So once this Enron was this energy company that went bankrupt in the U.S., in case you don't know, right? So it was a scandal. They really misled a lot of people. People lost their life savings on this. But the data was released, the data regarding who talked to whom, and even the content of the emails, right? Because there was an investigation. So we decided to look at this data, but not look from the point of view of the content. I don't care what they're talking about. Let's just look at the amount and how the structure of communication is evolving over time. So we chose, and this, of course, is just a simple picture. We chose something that says, okay, how tightly connected are we as time goes by, right? So because there is a theory in social sciences that says that at a time of crisis, you rely on people who are the closest to you, right? So if something is going on in your life, you search for your best friends to actually talk to. So I said, could we identify, or can we look at this? And we decided to take things such as clans and cliques, which doesn't matter, but think of it tightly connected structures, right? And then we were very surprised because we had these peaks And then when we went to see the actual investigation, the peaks occurred prior to what they called major events, right? So I think the 3 points there are basically the change of CEO, then the fire of the CEO, I think Jeff Scalings, and then the old CEO came back. And then I think the last point is when they actually declare bankruptcy. But the peaks were before and consistently about 2 weeks or so before the peak happened. So which we raised the question, it says, maybe, of course I can't really prove that, but maybe collectively people inside that company knew about it, right? Nobody knew it independently or individually, but collectively they knew something was going on. And once we plot this for the entire network, we see the peaks, right? I thought, and I still think, it was a very simple work, but you never understand what happens when you get a call from the national, so this was the NPR, right, National Public Radio, saying, I read your work, and can you give an interview? And I gave an interview and explaining what we actually found. And then this is just a sample. I still have some of the pictures. So this is a sample of people talking about us on the work there in languages that I think this is probably Hungarian. But I can only tell my name from there and the name of my student. You never know what actually catches the eye of the media. But basically, I was in the media trying really desperately to explain that I couldn't really predict the future. I couldn't tell that this was going to happen. I could tell that there was a tension there. Maybe it was something good. Maybe everybody was going to get a raise. I didn't know. I just said that there was a change in the structure. But it was actually a positive experience, which made me think maybe I can continue in that. Anyway, at that time, I said I was on my sabbatical. So then the second work that I did, and believe me, I'm not going to go through every single paper. But so I started working with Laszlo on this problem. This is a computer security problem that we were trying at the time to answer the question why we see an epidemic, we see epidemics of viruses in computers, but we don't see mobile phones. So we decided we had data about mobile phones, and we could know which ones were infected. So what you see on this part in here is basically the entire or part of the call graph, who calls whom, and the red ones are who are infected. And on the top are basically what we call the largest components, or the people that are infected that connect to each other. And you can see that they are very small. Right? So, and we basically explained at that point that the reason we don't see an epidemic in virus in mobile phones is because we have a diversity of operating systems, even when you look at versions of operating system, that is large enough to avoid what we call a percolation of the entire network. But we went further and we saw that we don't need a lot in terms of, if you like a clever guy in terms of writing a virus, if you write some virus that suddenly decides to randomly choose a number to copy itself, basically send you an SMS or an MMS, right, which is the one that includes a picture, you will go, and this is the dotted point, the dotted lines here are the random calls, you go from something that is completely disconnected to something that we say that the giant component is at the same scale as the entire graph. All right, so, and again, the timing was very nice because, I mean, maybe misquote in terms of time, but I mean, it was actually a few months, not many months after that, the first virus in the wild, as they say in computer security, was found that actually did random scans. So it was nice that our paper was published, that we said, well, this may be dangerous, right? Anyway, so we played a lot with, I started getting into some structure things. So this is one of the things that we did. I'm Brazilian, so therefore I wanted to understand Brazilian music, which, like, if you come from different backgrounds, you always think your music is special, like I think my one, I mean, from my country is special. But in Brazilian music, it's quite common that you don't have a single person that actually makes the music, right? So you have somebody who writes the lyrics, somebody that writes the actual music, and so there's a lot of collaboration. And I always had arguments with my dad because he comes from an old time that it was very easy to explain who was good and who was not good, because this is basically the network of Brazilian musicians in the 1950s, or at least who recorded it. And I try to explain to him that this is what really happens now. So it's a lot more complicated for us to really try to understand who is important. So we did some rank analysis, so we could actually show, at least try to show, who were important, right? And this is sometimes controversial because people say, well, music is about taste, right? I mean, I like it and that's it. And I said, no, it's fine. You can like whatever you want, but you can also like bad things and good things, right? So we're not discussing what you should like. I'm just saying, can we find a way to quantify the importance of a particular musician in that particular domain? So with Hugo here, when Hugo came to my lab, we played with trying to understand history and how historical characters are connected from books. You can think of this as some sort of a way to say, I could, if I wanted to say what should books actually be teaching. So I could have a distance metric between, if you give me a historic book today or a history book, I can say, does it have the same structure of what we expect, and how much does it deviate? And I'm not saying that's good or bad to deviate, but I'm just saying I can compare and have a spectrum there. So we can study even relationships. People done, for instance, if you watch the Game of Thrones, please no spoilers, I didn't watch this episode. But people have done work in terms of the Game of Thrones networks as well. Right, and again, trying to evaluate who is important there. I say, I know who's important, but we continue to do this. We went into, before anybody published that, right? And I think it's one of the failures. I never caught that was going to become important. Today there is this thing about the science of success, right? So people trying to predict how successful you will be. But we were already looking in 2002 and before on connections in computer science, and basically who is important based on who they collaborate, the diversity, entropy of their collaborations, and so on. It might sound strange, but I mean, we went from here to actually look at politics because it's basically the same thing. We are trying to say, think of a university like Exeter, right? So when I came here, Exeter became more network science than it was before, right? Maybe that was a bad choice, Ken, I'm sorry. But the movement of an individual influences the position of that group. So that could happen in science, but it could also happen in politics, and it happens all the time, particularly in multi-party systems like the ones in Brazil, where we can basically estimate that from a movement of someone from a party to another one, we can estimate what is the leaning in terms of left-right from that particular party, right? And which is what you kind of see in there. And we now have a paper under review that we actually propose a model that tries to capture what you see on top. Sorry, I'm moving backwards for some reason. Then we look at this, the last one before, I promise I'll talk about crime. So then we look at this problem of organ transplantation. So there were several other works, and at some point we were contacted in the lab and saying, we have this data from 1987 to today of every organ that has been transplanted in the United States. Because 1987 is when they started to actually track. And talking to some people, we started to understand how serious this problem is, right? Particularly in the United States. You can see, for instance, some of the statistics in here, for instance, 20 people die every day in the United States because they do not have access to an organ. So the more I read about this, the more I thought, well, that is something that could really have an impact, a real impact. So let's look into this, right? So, and just for comparison, the US is an opt-in system, which means that you have to tell that you're going to be an organ donor. And that's the same in the UK. As far as I know, it's changing in the UK. But somehow the scale of the problem there is really much larger. I wrote in here because I'm not very good at memorizing numbers, but So population of 66 million here. So you have approximately in the UK one death for lack of, so not having access to organ for every 165,000 people. In the US is one death for every 27,000, right? So there's more than just the fact that it is an opt-in system rather than an opt-out. So we said, okay, can we, since we think there is a structure everywhere, can we build a network of them? Right? It doesn't take a long time for you to think that, to realize that there isn't a network there, right? Because if I try to model who gave an organ to whom, then I need several generations of people, right? Because most of the organ donations are deceased donations. So from 87 to 2000, and this time it was 2009 when we published the first paper, I mean, we basically had one generation, right? And it was unlikely that if I die, that I give my organs to someone, that organ will have to be, could be utilized, for lack of a better word, again, right? Because there is probably a finite time that organ can survive. So linking people would probably not work. So we decided that we quoted this name called geographical social network, where we link regions. It's now very, very, very common, and I'm saying I quoted the name, but nobody uses the name I quote. But anyway, but it is, we decided to look at, and this is before the network, we decided to actually link locations where the links come, where the person came from, in terms of where the donor is, and where the recipient is. But like when we're doing data exploration, we decided to plot that, just to see, would the pattern show me anything? So that was before we knew how to do heat maps. So you can see that the red dots are organ recipients, green dots are organ donors. And because we're very good at finding patterns, sometimes that's actually a problem as well. But you can see that there are areas that are interesting. For instance, it turns out that the more urbanized the area is, the more organ recipients you have. Which basically, if you think in terms of an economy, in terms of supply demand, New York, for instance, does not provide to the system the same amount of organs that they actually consume. And we, again, when I presented this a long time ago, I'm not talking about where the transportation took place, but that is the address of the people when they register, basically the first time that they enter the system. Right? Even if they move, I consider the first time where they were, when they became in need of that organ. And the location where they lived when they became a donor. So we found those interesting things in terms of rural areas tend to be more green and urban areas tend to be red. So this shows the same thing, but we also wanted to find out where the organs are coming from, because the traveling of this organ is important, particularly for certain kind of organs like heart, for instance. So there's this thing called ischemic time, which is how long can the organ survive outside the body, right? And for heart is about 4 hours. So if we then look at the links between where the organ is coming from and going to, we could basically, using some sort of stochastic community detection, we could see if we see the network being more organized, like you see on the right-hand side, that's a good sign. What that means is that the organs in the orange area are staying within the orange area. And again, just goes back to my comment about me and my supervisor going to Cambridge and come back, right? So you have to remember the scale of this country. So a flight from Florida here, in case you don't know, to California, right? And of course I put Hawaii a little closer here, so there's Hawaii will be some other. But it's about 4 hours. So if you take in an organ and take it from Florida to California, it's unlikely that the organ will be useful by the time I get there. So this should not happen. So we wanted to see in practice, is it happening? Because there is a system that decides the allocation, so there is some sort of algorithm, but there is always the human in the loop, right? That basically gets a ranking, and then it is a medical doctor that goes there and says, no, choose the fourth person because I believe the fourth person is the best one to actually be allocated. So we wanted to see the organization of that. And for kidney, having this disorganization, which means that if you look at that, it's not so well defined as the regions here, it's okay because a kidney survives about 48 hours outside the body. Right? But funny enough is when we actually look at a lower granularity, this thing that looks very organized is not anymore. The lower granularity is now I'm linking zip codes. And then you see the regions in the kidney much more well defined. In fact, this picture here was the one that actually I think got the paper accepted, is because we indicated that this area here, the purple one, or magenta, if you're picky about it, that area should not exist because the US is predefined, is pre-divided into regions. So this magenta is supposed to be the same color as the red one. And we argue that those three states are Alabama, Mississippi, and Louisiana, the largest concentration of black people in the US. So the point was, could it be that the human in the loop is adding some sort of racial bias to it? That once you choose the person in the list, if you are black, you choose people who tend to have black names, and if you're white, you tend to have people who are more Caucasian in terms of their. Okay? So, and before I get to crime, that got us interested in flow as well. So we started actually expanding the work in the lab in terms of human dynamics, which is something that we use now, that we do quite a lot of work. I mean, with Hugo, we proposed this model that says that when you're trying to model human behavior in terms of how we move around, you have to consider how recent we've been to a particular location, which is more likely that I'll come back to a recent location than a frequent location. So I'd like to put this way, and Hugo is here perhaps to correct me, I'm sure, which would be if I have two locations, one that I've been frequently but not recent, and one that I've been recently but not frequently, I most likely will go to the one that is recent but I've never been before, right? And we thought that this model captures some of the errors that the model before us from Chao Ming actually didn't. And then we had this last one before I talk about one, right? And I tend to put this one because, again, Hugo is here to confirm. He comes to the lab, and I said, Hugo, I had a dream, not like Martin Luther King, but I had one where I would never recommend people, I always do this joke, but I don't recommend people doing science by dreaming, right? So, but, and I have this tendency to have things next to my bedside that if I wake up and I write something, never worked except for this one. So where I had this dream that I was actually walking from Facebook to Twitter, right? So I asked him the question, I said, could it be that we actually surf the web in the same way that we actually walk, right? So could we have the same regularities there? So he did all the work, and then what you see, and some other time I can give a talk about this, is to show that the regularities are quite similar. They're actually strikingly similar. Anyway, now I'm into human dynamics. Finally, talk about crime, and I'm gonna try to be fast, right? So crime is everywhere. There are different types of them. So it's quite amusing to actually see those videos on YouTube, right? So you can see, and I tried to choose one that the search give me a burglary, which is the one in black and white, a robbery, which is the one here on the bottom on the left, and theft, the one on the top. The theft one is quite amusing. I can watch that so, because that's a wig store, right? And just that by itself already makes it interesting. But you can see people trying to leave. But I mean, there are different types of crime, and we're trying to understand how, I mean, is there any regularity in this, right? So is there any predictability in those types of crime? And then I'm showing this because you're going to see the next slides. I'm going to show results that talk about theft on top, burglary, and robbery. Okay. It's everywhere. There you go, Anya. I told you that there was a picture about a bicycle. So the bottom right-hand corner is the number of bicycles that are stolen in London, right? So, but you can collect this data. This data is actually being collected by the police forces everywhere, right? So you have You can plot heat maps of crimes. And you have the U.S. and London. They're different. This is basically violent crime in London in here. So let me do this. Sorry. Right. So on the left-hand side is violent crime, and there is bicycle, and they have different patterns. So this is why we want to study them differently. A lot of times when people say there are a lot of crimes in X, they tend to look at disaggregated, so we like to disaggregate. And of course, we live in a time that this data is being collected everywhere, so that's only that picture there. So this is, maybe I'll show you here. This is Los Angeles and how they actually look at the history of crime, and you can faintly see the map and the peaks, so they have some nice systems. Rio de Janeiro apparently is actually having one of the most advanced systems in terms of tracking crime, but the data exists, right? So anyway, so I told you that I was going to come back to that, but since I already told you this story about this first work that we did in crime, I'm just going to say that here, this part of the equation here is when we consider the communication between the criminals, right? So the whole thing that we did, this part is the unsuccessful part, and when we added this component in terms of the social communication, the model became more precise. So I can skip that. I don't know if I have questions then if you want. Right, so now we're trying to say, okay, that work was crime against property, right? So where we assume the location where the crime is taking place doesn't move, right? But now when we're talking about theft, or we can also consider people moving in the city. So we'd like to expand this a little more. Why cities? Well, because since 2005, we have more people living in cities, and the trend will be for us to actually have more and more people living in urban environments compared to urban. And of course, we also have data from many different sources. So this is just a picture that we do. This is basically tweets. So we can collect data from where people are tweeting, and so we know something about the population. You see later, we can't use that data for criminals because only a few of them, you'll be surprised, only a few of them tweet that they actually committing a crime. But they do, but it's not enough for us to actually do the study. But I mean, there is data from incidents. So the first thing we did was to actually look at structure. I skip this, but we tried to basically say, let's take something very simple, right? So look at the location, take the data from the police, look at the location where the crime is taking place, and link the two events if they are at a certain distance or within a radius. So we can do that, and I said, because I'm probably talking too much, we did this for several cities, and then once we correlate, so once we have this structure, by the way, so I'll just come back here a little bit. Once we have this structure, on the right, we can partition it using what we call community detection, and that is what gives us these borders, those borders. So we can correlate the borders now with some socioeconomic factor, right? And when we do that, it's quite surprising that it matches quite well, basically saying that the borders seem to appear where you see a difference between socioeconomic factors of the people there, like education, income, and so on. So we use here a vector of several indicators. All right, so, but the title of the talk is scale. What is the title of the talk? Scale, concentration, and dynamics of crime, right? So let's talk about scaling, right? It's not me. I mean, Bittencourt and the guys from the Santa Fe Institute, they showed that the many urban indicators is scale with population size. What they pointed out was that there seem to be two different categories. You have this growth that the growth of this indicator is generally sublinearly if it is related to infrastructure in a loosely way, and is superlinearly if it relates to social aspects. Quick example, if in Exeter today we, let's say, have 50% more people, I don't have to build 50% more roads, right? Because the roads, we can share them, okay? However, on the social aspect, for instance, the creation of patents, for instance, we will actually have a superlinear growth because if I double the population of Exeter, I will have generally a double because I increase the number of people in terms of number of patents generated, but I also have the patterns that are generated from the collaboration. All right, so we have this social aspect there that this gain. This is why they grow super linearly. And unfortunately for us, crime is in that super linear scale. So as population grows, we have a superlinear growth of crime. So this is important. I mean, don't get me wrong. I mean, it's important also to really understand that and understand this for different types of crime, because once you read on your news on BBC that it says that we have 3 crimes per 1,000 people in Exeter, and we have 4 crimes per 1,000 people in New York, you can't really be doing this. There is a bias there, depending on the type of crime in particular, because I mean the growth is super linear. So you can't be comparing those two things because you have more people there than here. All right? Again, we have to be aware of this because we are comparing most of the time. There is not saying comparing apples and oranges, but we're comparing. We can't put those things in the same sentence. Right? So we have to be careful. That's what this slide is explaining. So this beta value here is what tells me if they grow superlinear or superlinear. So when we started looking about crime, we said, okay, let's look at beta include result, and let's separate by type of crime. We separated here, so you have UK on the red there, all right, so just for theft, and then we have the US burglary, robbery, and theft, and you see we found nothing interesting there because we said, well, it grows super linearly like anything else. Well, it turns out that it's not that simple. We have a work that shows that certain types of crime is not superlinear, which means that for burglary, it may make sense for you to talk about per capita, but for theft, maybe it doesn't, but I cannot talk about this because it's not published. So let's move on. Right? So that is in terms of concentration. So there are differences in terms of how different types of crime concentrate. For how they scale. The next one is concentration. One thing is to say there is more crime because there's more people, but the question is where are they taking place, right? And there is a work, I guess, from the 19th century that says that, of course, the crime in cities is not distributed uniformly. There are places that will have more crime, places that will have less crime. So that's not what we're trying to do. We're just trying to say, how can we quantify it? Can we give it a number to it? Right? So we basically, we're trying to basically look at, can we actually characterize those differences that you see? So there is an aggregation problem, because if I want to eliminate the population in that study, I have to make sure that, because I don't want to say that there's more crime, I want to say that there is more concentration of crime independent of the population. So we had to find a way first to just divide the city. So we use census data, so we know where people live, so I can take a city and I can divide into areas that have more or less the same population size. Now, if the concentration, which is basically say the amount of crime that is taking place in that location, is directly related to population, if I divided my regions into populations of the same size, I should have the same number of crime events. Right? So we do that, and in fact we do this several times. We take a city, we generate random points, we generate some sort of Voronoi tesselation of this, which is not relevant, and then we can generate a graph, which are basically the locations that are linked to each other, and then we can partition this graph in many ways we want. So we use data from many cities, because as I told you, criminals don't tweet, so we have to get data from the police, but we've done this for several countries. This is just one example. And then to look at concentration, we use the known Lorenz curve, right? So which you're familiar with, which tries to actually measure inequality. I mean, it's, do this. This one here, I mean, the way you should read this is that 20% of the, if it is equal, 20% of the population, let's say, has 20% of the income. Right? So that's what the curve says. So since this has been used in the past to talk about inequality, let's look at inequality of where the crimes are taking place. So we took a city, and this is Chicago, and then we plot basically the curve for, and then we can see here, for instance, 20% of the regions have almost 0% of the crime events. So you can see that crime, so let's say the the more prominent this curve is, the more concentration you have. And we saw for this city that theft, burglary, and robbery concentrate differently. One city, right, doesn't tell me anything. So let's do for several cities. And then once we actually put the colors there, you can see that there is a very well-defined difference between the types of crime. Okay, but this is just visually, we want to quantify this, so we can actually plot the probability distribution of a particular region having more than a certain number of crime events, and then use, and once we do that, we can show that most of those, that those distributions can be explained by a power law, and then we can use this exponent as the characterization of the concentration. Okay? And again, that's the part that we do in terms of concentration. We did this for every city. What you see here in terms of this kernel density estimation is, you remember that I divided the city in many areas. So we did this many, many times. So which means that for every division we have a different sort of exponent there, but it's quite consistent, particularly for theft. Right? But the point is that you can see that the blues are before the oranges and before the greens. So theft concentrates more than robbery, that concentrates more than burglary. Okay? And that's how we're trying to quantify. We took that mean point here, right, which is those the dots there and squares and diamonds, and then we tried to do an independence test with population. And I think this is the first work that actually shows that the concentration of crime is independent for all of them to the population size. And what does this mean? This means that when you look at how crime concentrates in New York, could be similar than how it concentrates in Exeter. So basically New York City is nothing more than a collection of small Exeters. Right? And that's what we basically saying. Why is that useful? Well, because we think that the police can use that information to decide what sort of countermeasures they actually need to actually make. What about dynamics? Right? Okay. So I told you something about the scaling. I told you something about how it concentrates. But if I tell you that there are hot spots in a city, I didn't tell you if that hotspot changes all the time. Maybe that hotspot area is always hot, but maybe what we see is some sort of wave effect, right? Where I always have areas that are very hot, but they change. So we wanted to actually look at how what is the dynamics of that. So I hope this picture can be understood. But what we have is that, think of a region, right, at a particular time. This is time there. So and then this is the most, let's say, the area that is the hottest one in terms of number of crime, the second hottest, third hottest, and so on. Now what I want to see is how this changes over time. So I see, would this orange, this region, remain as the top one, or would it change as I progress in time? Right? So if I see the orange repeating itself all the time, I see that there is basically this is more stable. And we can use some sort of channel entropy to actually measure that. Right? So what we did, we actually look at those columns there. We have now a distribution of the regions, and from this we can actually calculate the entropy for each of those columns. So I go to the next slide, which now you can see that's the same graph as you had before. So you see that you have different characteristics for different cities. Try to say this again. What it means is that I now, if I'm the mayor of Portland, let's say this one there, I do understand by looking at this chart the dynamics of crime in my city, which is completely different than the dynamics of crime of Kansas City. Or in other words, which mayors tend to do this all the time, they said, well, you saw that they implemented this in New York, or they implemented this in Chicago, and they reduced crime by 50%. I should do this here. Well, you don't know that. You don't know if the dynamics of the crime dynamics in your city is the same. So what we're trying to do is to say, if you're Portland, and you want to actually do something, if Chicago has done it, perhaps you should imitate that, because you have a similar signature of dynamics. Right? That is better, in our opinion, than actually doing it blindly. On the right-hand side, you see that there is also difference in terms of this dynamics on positions in terms of theft. So theft tend to be more stable. So if you have a hot spot of crime, for theft, it tends to stay that hot spot. For burglary, which is you have this high entropy there, right? It doesn't. It changes all the time. Which, if you're sleeping, it comes. So we can no, we'll skip this. We can cluster cities so we can help people doing decision making. But if you're sleeping, comes to the exam question, right? Because if this is an inaugural lecture, I have to have a written paper at the end, right? So if you've been paying attention, you should look at those two pictures, right? And you should actually tell me which type of crime is the one on the left-hand side, and which type of crime is the one on the right-hand side. Can you? Which one, Jack, is the one on the left?
Burglary.
On the left?
I forgot which one the difference between burglary and theft is.
Right. It's
Theft.
more
It is,
stable,
you see,
yeah.
because she has to ask the question in the end, so she's been paying attention. So, thanks, Gracie. So, it is theft because crime concentrates more than it concentrates on the right. So you have theft on the left-hand side, and then burglary on the right-hand side. Anyway, take-home messages, right? So crime is not as unpredictable as you think, particularly when you look at the aggregated level, right? The concentration of crime is independent of population size. We need really evolving policies for curtailing crime that will use real-time data, right? That we actually collecting all the time, and we also use the models that we are proposing. And working against me here, but I need more people to work in crime, right? So I need competitors. I need people to actually start looking at this data because there is a lot of data related to crime, and it's not being looked at, right? So some things that we're actually trying to do, we're actually looking at now to measure the predictability of crime. So if I say that crime is predictable, is burglary more predictable than theft? So, but how much can I actually put a value to it? Right? So we actually have a paper ready. I'll show you the link later about using wavelength theory to actually show that there is a neighboring effect. If I reduce crime in this particular location, it tends to spread to the neighboring areas, so it doesn't spread randomly to across the city. Right? It's quite difficult to actually deal with other types of crime, particularly things such as rape, because there is a privacy issue there. I mean, it's a serious crime, but a lot of people don't report, right? And when they report, we don't know the information, where it's taking place, and so on. So it's difficult for certain kinds of data. But I wonder if I can have another dream and then tell Hugo to look at if online crime is the same as real crime, physical crime, and if we have similar patterns. Last, we actually work with the federal police in Brazil, and this will be published soon. Hopefully in the future I'll have time to tell you about this. It has to do with pedophilia in online forums, and there are some quite interesting results there that we hope to tell you when we publish. Right? So it's disturbing. When we start working with the police, they said, well, they also have data of images, right? And of course, try to make sure that that is one thing that I don't want to see, right? So I don't need that, never, but they do the sting operations that and then they can track where people are and what they are watching online. Anyway, so those are my partners in crime for this work. And I have to finish here very quickly by saying this is all the people that I could find a picture that has ever worked with me, and I really have to thank them all for support and inspiration, for discussions and fights and so on and so forth, right? So I'll finish it here, and I'll take your questions if you have any. Thank you very much.
Okay, so
And I can guess my ones.
I did pay attention. Thank you very much for the really kind of interesting and fascinating overview on what we can learn from data. Your love for patterns, which I kind of share. It's really close to my heart. as well as kind of the quest to quantify and to try to give insight.